Welcome to Group 2's presentation for our glucose monitoring system. Our group consists of myself, Selena Bergi, Hugo Acosta, Mark Rodriguez, and Brianna Moreno. Hugo Acosta is the team lead, being responsible for monitoring the overall project and ensuring all of our goals were met. The customer interface and support manager was myself, Selena Bergi, which included keeping the stakeholder perspective in mind and verifying that these perspectives were shown throughout the IVV process. The planning and quality manager was Mark Rodriguez, who ensured that the entire project was planned properly and followed all rules and regulations. Finally, the design and support manager was Brianna Moreno, who ensured the project design matched well with IVV techniques. This was our schedule for the course, starting with the concept phase, which includes the concept of operations, or ConOps document. This was the main focus of the concept phase for this course. From there, the requirements definition phase allowed us to define our requirements and verification validation techniques for each requirement. Then, the design phase allowed us to make sure that our design was justifiable and followed budget requirements. And the integration and testing phase allowed us to come up with the testing plans for our system components, integration, and qualification acceptance. The final step for this course is to complete the final IVV plan, defect log, and reflect on our project. But for now, I will review the beginning of our project with the concept phase, which will require information from our ConOps. The concept phase allows the team to observe a problem and brainstorm ways on how to fix a problem. The ConOps is a document in which a project team can record how the current system works, the problems with the current system, and the justification and technicalities of the proposed system, along with any trade-offs or alternatives. In our case, the current system for taking glucose measurements requires a diabetic patient to prick themselves in the finger multiple times a day to get one measurement. It also requires the patient to manually write down each measurement with the time and date, and the measurement can only be taken in a sterile area to avoid infection. Not only that, but the current glucose system is expensive, and it requires diabetic patients to make visits to an already oversaturated doctor's office. Our proposed system plans to use modern infrared sensor technology to create a non-invasive glucose system. This will eliminate any pricks of the finger for diabetics and will no longer require them to take measurements in sterile areas. They will be able to take measurements as many times as they want in a day without having to draw any blood at all. The system will also be able to automatically log all measurements, and it will be wearable so that the user could take measurements from anywhere, since the system is non-invasive and doesn't require sterilization. They could even use it while exercising and sleeping, which is something that current systems cannot do. Lastly, the proposed system can take the measurements and create reports to send to the diabetic's physician in order to potentially eliminate doctor's visits altogether. And this system will overall be cheaper than the current glucose monitors, which require constant buying of test strips, glucose meter lancets, and other equipment. The purpose here is to create a system that is easier for diabetics to use, which will ultimately give them an increased set of glucose data that can potentially improve their care plan and help them prevent the side effects of diabetes, such as hyperglycemia. It will also extend the diabetic's healthcare to anywhere because of the wearable and non-invasive factors. This system will be a non-invasive wearable device that can monitor glucose levels on type 2 diabetic patients ages 18 to 45. It will also provide data trends, visualizations, and two-way communication between the patient and their doctor. It will consist of 3 subsystems: the actual wearable device that takes the measurements, the mobile application where the patient interface can help the diabetics view all their measurements and communicate with their doctors, and the secure network, which provides the communication between doctor and patient and provides secure transmission of patient medical data. Shown here is a visualization of the data flow of the glucose system. It starts with the biosensor system, which will allow the device to non-invasively measure glucose readings multiple times a day using a small, harmless infrared sensor. Measurements can be set up to run automatically or can be taken manually by the patient, all with no prick of the finger required. This device will show the user every reading on the wearable device, notify the user if their glucose levels are too high or too low, and will store the raw data readings in the database. The app will retrieve the measurements from the database and provide the reading reports in the application for the user to view. A history of data measurements can be directly sent to the doctor as requested before the patient appointment, or maybe even in lieu of any appointment, using the network and email system. From there, the doctor can also send emails back to the user to create two-sided communication. This device will also be wearable, so it can be used while sleeping, exercising, or general places visited by the patient throughout their day. Here is a use case diagram for the entire system and all of its users to further explore the system flow and purpose. The diabetic patient will be able to take measurements, view their data information, wear the device, and basically use both the wearable device and the mobile applications interfaces to interact with the system. The doctor will be able to only interact with the communication interface of the system in order to view the patient data and communicate with the patient. The technical support staff will be able to access the back end of the system in order to troubleshoot and perform maintenance on the system to provide the customer with the best service possible. Lastly, the software developers will have access to the entire system security in order to update and check the system security. In order to keep any project free of defects, a defect removal process needs to be established in order to check documents throughout the product lifecycle. In our case, defect removal was done when documents were completed by each member, and then peer-reviewed by at least one other student from the class. Checklists were used to find defects as well, mainly in the system requirements, in order to ensure that the requirements were unambiguous, consistent, complete, singular, feasible, traceable, and verifiable. Every defect within any of our documents throughout the entire class were recorded in our defect log. The top picture on this slide is an example of the checklist we used for our requirements, and the bottom picture is a small sample of our entire defect log.
This is a risk matrix for a glucose monitoring system. Each risk ID represented in the matrix can be tracked to the risk descriptions in the risk table, which will be shown in the next slides. For example, risk ID 4A, which is located on the bottom left box, has a risk description of device malfunction, no customer support, which can be found in the risk table. By observing the risk matrix in the previous slide, exclusion factors, probability, and impact, the best mitigation handling methods for each risk description can be determined and a mitigation plan can be created. This table shall be observed weekly to monitor any changes that may occur to each risk that are listed in the table. The table describes the risk, detail the risk parameter values, handling method, mitigation activities, and the person or persons responsible for the activity and risk. The exposition factors were determined as follows. Factor less than or equal to 11 risk will be accepted or mitigated. Factor greater than 11 mitigation activities are planned and enacted. And factor equal to or greater than 20 contingency plans are created and the mitigation activities continue. This slide is a continuation of the risk table shown in the previous slide. As can be seen from the table, most of the risks are acceptable and either already have mitigation systems in place or simply need to be monitored because they are not likely to happen. The risks we need to pay attention to and actively need to mitigate have to do with system failure and overdriving the cost of the product. These are major risks that are more likely to happen that need to have mitigation plans in mind. The only major risk that would be most likely and very impactful is a breach in our security, resulting in the loss of patient data. In this case, we would need an emergency contingency plan to try and counteract as much threat as possible. The system requirements were broken down into subcategories: functionality, communication, cost, performance, safety, testing, compliance, maintainability, reporting, security, documentation, traceability, and electronics. The requirements were essentially based on what is needed to build the system, what the user needs, and what the system needs to comply with FDA and HIPAA requirements. This is a continuation of the requirements you saw in the previous slide.
Now, let's describe the requirement verification matrix. Requirements need to be reviewed and verified following a set of defined techniques. These reviews and updates of the RVM will occur at the end of each lifecycle phase. Our current RVM consists of 70 requirements. Using this updated list, it was determined at which stage of verification each requirement should occur at. For example, one of the requirements specified for training costs should be verified at the beginning during the definition phase and later during the integration phase in order to make sure the project does not go over budget. There will be 5 verification stage categories. These are definition, design, implementation, integration, and qualification. The applicable technique is chosen based on which verification stage is chosen for the requirement. For example, if the verification technique chosen is inspection, verification tests can include visual checks or fake-in inspections. Finally, the personnel assigned to work on the RVM will be as follows. The team lead and planning manager will integrate the RVM, while the process managers and planning managers will review the RVM. The following is a sample of the first 4 requirements analyzed by the RVM. As you can see, the RVM is subdivided into different fields. Each requirement has a unique requirement number, a traceability number, a field for describing the requirement, the verification stage in which the requirement will be verified, and finally, the level of the requirement at the component, subsystem, or subsystem level. Let's take the first and third requirements as an example. The first requirement of our system reads, the system software shall be highly reliable with no more than 1 failure per 1,000 hours of operation. This requirement must be verified at the qualification stage, and this requirement is considered to be at the system level. The third requirement, on the other hand, reads, the system shall be accessible through any smartphone with Android and iOS operating systems. This requirement must also be verified at the qualification stage. However, this requirement is considered to be at the component level. Please refer to Appendix B of the IVVT plan for the full RVM. Now let's take a look at the requirement bidirectional traceability matrix. For our RVTM, we broke down the system into elements and sub-elements. The main elements were the main components of the system, such as the wearable device, network, and mobile application. Each element was then broken down into their own sub-elements as well. For example, the wearable device was broken down into the sensor, device shell, Wi-Fi module, microprocessor, etc. Once the elements were defined, forward and backwards traceability were determined from each of the 70 requirements to each element. Every requirement was forward and backwards traceable with at least one element and vice versa. Thus, all of our requirements and elements are justified and traceable. Shown here is a small sample of RVTM showing the traceability of the wearable device subsystem with the first 19 requirements. As you can see, the main element of the system was broken into different components. In the case of the wearable device, it was broken into the sensor, the device shell, which is the bracelet, the connectivity modules, the microprocessor, PCB, power and battery, product support, and user manual. In the case of the first component of the wearable device, the sensor, you can see that there is a forward traceability and backward traceability with requirement number 2, which is defined as the system reading shall be accurate 95% of the times employed. For the full RPTM, refer to Appendix C of the IVVT plan. The cost-benefit analysis takes into consideration the risk identification that was performed during the development of the system, as well as the probability of occurrence and severity of the risk in order to calculate the total factor of probability and severity. After calculating this factor, the cost taken into consideration was the cost of performing the testing for each risk to confirm integrity over the life of the product. Then, the appraisal cost was estimated based on the cost of rework and the probability of finding faults in the system after testing them. Finally, the impact cost was estimated based on the cost of the impact caused by not testing the risk at all. Using the total cost and factor values, it can be identified which risks are more important to test than others and the cost of this testing. Here is a sample of the cost-benefit analysis done for the system that shows the security risk of the device. These are the highest factor risk with the highest probability and highest severity factors. As you can see, the VVT and appraisal cost for risk 11A, defined as security system fails, has an estimated penetration testing that costs around $7,000. However, the impact cost is much higher because the repercussions for a data breach are very drastic, including any lawsuits, for example. In conclusion, the risks are very great if the security in the system fails. For a full look at the cost-benefit analysis, refer to Appendix A of the IVVT plan. The implementation phase begins with the component interface analysis. In terms of component interface analysis, the purpose of the GMS is to ensure that when glucose readings are taken, the information is accurate. Additionally, if the glucose reading comes out too high, the device can effectively notify the doctor. Any errors or miscalculation in these areas could cause harm to the patient. Thus, extensive testing needs to be done. Component testing at this level includes the components of the sensor assembly such as the IR sensor, the photodiode, and the amplifier. Glucose readings must be obtained from different samples of diabetic patients and under different conditions such as fasting, 2 hours after eating a meal, and before and after 30 minutes of reasonable exercise on a treadmill. The measurements will be taken with a non-invasive sensor and with a commercial test strip glucose monitor in order to establish a baseline for what the measurement of the patients are. The purpose for conducting testing at different times is to be able to obtain samples of different glucose levels ranging from below 80 mg per deciliter to above 250 mg per deciliter. This is a diagram of the many component interfaces that make up our system. For example, power, the user, the mobile application, the cloud and backup storage, the mail server, and the medical expert. As you can see, the brown circle highlights the components of the sensor. As mentioned before, the components of the sensor consist of a 940 nanometer wavelength IR sensor, a photodetector, an amplifier, and a microprocessor in charge of computing the calculations of the glucose level measurements. After the measurements are computed, the microprocessor interfaces with the device's display to show the obtained glucose levels and also interfaces with the local storage of the device to store the readings for quick future access and histogram displays.
(7.4) Integration phase. The goal for this glucose monitoring system in terms of integration is to ensure that when the whole system is integrated, there are no errors among any of the items in the system. It also ensures that requirements are fulfilled by this integrated system and that data flows within the system as it's supposed to. Any errors in these areas could cause harm to the patient. The integration test that was chosen to complete was penetration testing between all subsystems because it was identified as the most critical. These test risks required information testing on network, database, application, and the wearable device. The integration test covers the security system of the integrated glucose monitoring system. The items to be tested will be access control of patient data, storage security, and transmission of security data to the system. The only feature to be tested in this test is the data security of the entire system when operational. The approach was that data security as it is used by the device, network, database, and application will be tested. And the test will be done on a fully integrated and safeguarded prototype system that is not in production yet. Penetration testing of the glucose monitoring integrated system will be evaluated and determined to be passed if the subsystems successfully deter any attempted penetration of the system by the testing team. An end-to-end penetration test analysis will be completed, which will be an analysis of the communications of the entire system. The test deliverables will be as follows: test specifications document, test plan document, traceability matrix, test reporting status, and a defect log. (7.4.2) Built-in testing, or BIT. BIT tests are one way to perform integration testing. They are especially useful for monitoring and controlling systems. A critical aspect of our system was identified through our CBA, which in this case was the microprocessor's capabilities of assessment of glucose measurements, performing access control functions, and connectivity capabilities. These are integrated tests that can be assessed using an automatic bit on the microprocessor while the system is being operated by the user. Integrated test cases. This test evaluates the assessment capability, access control, security, and connectivity capability of the measuring device's subsystem's microprocessor while it was online and operational. The test that will be physically tested is the measuring device itself, which is a bracelet that the user wears in which glucose measurements are made. The features being tested are the functions performed by the microprocessor. The test will be done on the bit controller of the measurement device that is fully integrated, safeguarded, and operational, and being used by the diabetic patient. The microprocessor is the main component being tested for its functionalities. For assessment capability, the test will be seen as passed if the following microprocessor alerts patient correctly for glucose measurements. All test cases and test scenarios have been executed, and the test deliverables will be as follows: test specifications, documents, test plan, traceability matrix, status reports, and defect log. 7.5.1 Qualification analysis. The qualification testing for the system is required once the system has been produced for final testing before production can occur. The system must pass all qualification tests in order to move on in the process. Integration test cases. The qualification test will require a security audit of the fully integrated and operational glucose monitoring and its operating business entity that runs the whole gamut of including IT, customer support, etc. For the security audit, the following test items are needed: the measuring bracelet device, mobile application, network of the system, the user-doctor communication system, and the business entity that provides the system, the IT department. All will be assessed in the security audit. Features being tested in the security audit are the network, operating, and physical security of the entire glucose monitoring system and its operating business entity. The approach is security vulnerability, employee interviews, access controls, physical access to the system. As data is being shared, it will be tested and assessed in this audit. The plan includes criteria for pass-fail assessment capability and access control. Details can be found in the document. An end-to-end test analysis will be completed, which will be an analysis of the security of the entire system as the and criteria and test deliverables. (8.1) Maintenance purpose. Maintenance will help ensure the system continues to satisfy its objective. The purpose of the maintenance is to sustain the capability of the system enhancements, upgrades, and modernization once the system is already launched and operational. Maintenance types. The types of maintenance that will be required for the GMS will be as follows. Corrective maintenance. This will consist in following processes and procedures for restoring GMS services to normal operations, including such actions as repairing a faulty sensor, replacing the wearable wristband, recalibration of any uncalibrated sensor, etc. Preventive maintenance. This will consist of the following processes and procedures for scheduled routine maintenance actions as required by the GMS. Maintenance levels. The GMS will undergo user operator maintenance in the form of routine and simple maintenance tasks able to be performed by the user as explained in the guide manual, and factory maintenance. (8.3) Disposal. The disposal process is to remove elements from the operation environment with the intent of permanently terminating its use, and to deal with any personal information, data, and collected products, artifacts in accordance with applicable guidance, policy, regulations, and statutes. The disposition methods. Operational phase is some disposal of GMS elements and components occurs during the system's operational life. This happens when the tested elements and components fail and are replaced. Retirement phase. At the predetermined time of the original GMS's retirement, a decommission plan will be adopted to bring new systems online that operate in parallel with the existing system so that service interruption is kept to a minimum. Number 9, conclusion. The purpose of conclusion is for verification and validation process to identify specific test and analysis process for reliability, safety, and performance of the GMS system. The goal to be satisfied by this VVT plan is the successful verification and validation of performance and safety requirements specified and to identify potential risks that will require risk management effort. In conclusion, the IVV test plan for the GMS will be evaluated for final determination to commercialize the system as a patient care device selected by users and health professionals as a meaningful and value added to assist in the monitoring of glucose levels.